Okay, now before I start into the amazing discovery made by Ørsted, I want to clear up one thing that I said in the last class that I think was misleading. I said that you could get more current if you made the battery bigger. Okay, that was very ambiguous, because what do you do to make the battery bigger? Do you just make the plates bigger, or do you make your stack bigger? Well, it turns out that if you make your stack bigger, that does increase the current. If you just make the disks bigger, that doesn't increase the current. What it will do is it will make your battery last longer. Okay? So, yeah, Ben.
For having bigger stacks, it would make it last longer.
Well, no, bigger stacks
Or
will
bigger-
make it the current bigger. Okay, more electric current.
Bigger discs.
Bigger disks will make the battery last longer, so it'll put out current for a longer period of time, but the amount of current it puts out won't be any more. Yeah.
What if they were like really long, like wide discs? Would it?
Oh, what matters is like the surface area of the disk, not the exact shape. Okay, so it doesn't have to be circular like the ones that Volta used. I mean, it can be long as it's the amount of surface area that is against the saline or acid solution and then in contact with the other metal surface. Nick.
Well, you had like a theory, but like on how it worked. But
Oh,
I need to
yeah.
know, like in Franklin's theory, like if something was bigger than something else, is there more fluid in it, or are they just the same?
Oh yeah, I'm glad you asked that because I meant to make the connection back to Franklin's theory. Well, so before we start into this, I'm going to go back to electric batteries.
Should we probably erase
and-
Hans Christian Ørsted?
Hmm?
Should we probably erase Hans Christian Ørsted?
Yeah, you can save him for later. I'm going to get to Nick's question in a minute about the connection to Franklin's theory. But so the first point that I want to make is that, let me see, the this big, yeah, I mean, increasing,
And bigger stack.
let me see, increasing the stack of metal plates increases the electric current.
Would we say increases the conduction of the electric current?
It will, increase the magnitude of the current. So you can charge up your Leyden jar more. You can create bigger sparks. Okay, and that's how, at this stage, that's how they were testing, how strong a current they got. The other thing that will increase the current, what do you think would be the effect of changing the thickness of your wire? I mean, let's say we have a stack of batteries here, of these plates, and we have a wire, connecting the top one to the bottom one. What if we made that wire twice as thick? What do you think would happen?
It decrease?
Decrease the current?
Yeah, because wouldn't it move easier through a thin wire?
Oh, you think it would move easier through a thin wire. So if you get it really, really thin, then it would have a lot of electricity. If you got rid of the wire altogether, then Then it would be enormous. No, see, it's the other way. If you increase the thickness of the wire, I mean, it's just, think of water going through a hose. I mean, there really is a parallel here. I mean, if you increase the thickness of your hose, you can get more water through it, right? Well, it's the same thing with electricity flow. If you increase the thickness of the wire, you can get more electric current. Troy?
Would it run out more quickly?
It would run out more quickly, absolutely. Anything you do, I mean, if by increasing the thickness of the wire here, you get a faster, in essentially a faster flow of electricity, well, then the amount of electricity that this stack of plates is able to generate, it will just go through that amount of electricity faster. So it's like you have going back to the water analogy and the hose, it's like what these plates have. I mean, the parallel would be you have you know, a certain reservoir of water, okay, a pool of water, okay, and you're pumping it out through a hose. Well, you can have a bigger hose and pump it out faster, but you'll go through your water faster. Okay, Troy.
What was like the biggest stack that was, do you know?
Oh, I don't know. I know that there was an English chemist, Humphrey Davy, who had an absolutely enormous battery, but I forget how big it was. I'll look that up for you and tell you in the next class. Neve. Oh, so, but the surprising thing is that just increasing the size of the plates doesn't, like I said, increasing size of metal plates
And you say makes the current last longer.
right, makes the current last longer, but doesn't increase the magnitude of the current. So, yeah. Okay, so I didn't make that clear. Yeah, Selah.
Why does the size of the metal plates make the current last longer?
Oh, well, I mean, I guess you can think of it as if you go to the water analogy that I'm using, it's like increasing the size of your pool. Okay, so basically what you've got is, I mean, let's picture it this way. We've got this pool of water. We got a pump, okay, to pump the water out through this hose, okay? Now, what matters in terms of now, if we increase the size of the pool, it'll take longer to pump the water out, right? Okay, so that's exactly, so we'll have water going through our hose for longer. That's exactly like increasing the size of these metal plates. That's like increasing the size of the pool. In other words, by increasing the size of the metal plates, what you're really doing is increasing the size of your reservoir of electricity, basically, how much electricity you have available. But what matters in terms of the flow, the rate of flow of, say, the water in my example is the strength of your pump, right? Okay. Now, the strength of the pump in the electricity case, that's like how many stacks of batteries, how many batteries you stack together. See, each one of these zinc silver combinations gives you a certain amount of power. And every time you add another zinc and silver plate, you're increasing that power. I mean, if you have one plate, just one, silver zinc plate combination, okay, that's going to give you so much power in your electric pump, in effect. And if you throw in another couple of plates, you'll double your power. Throw in 3, you'll triple your power, and so on. So what they used to do to make powerful batteries at this stage was, this guy that I'm about to tell you about, Ørsted, he used to work with a battery that was, a stack of 20 of these things. So 20 pairs of zinc silver plates.
What happens if there's just a wire connecting from the top to the back to the bottom to the bottom? It's not running off.
Oh, if the wire is just directly connecting the top and the, well, then you'll get a strong current through that wire.
But so would it ever run out if you kept it like that?
Oh, yeah, it would. It would. Oh, you think you're taking the electricity out and you're putting it back in, is what you're thinking. But what is creating that electricity is, so that's a way in which the water example is different than the electricity example, because the what's driving this electricity is a chemical reaction here in these plates that eventually it uses up like the silver and the zinc, and so it stops pumping the electricity. Yeah, Troy.
Would it make a difference? Well, I don't know if this is Nick's question, but it might be if you just didn't have it connected to the wire connected to the bottom.
Yeah. Well, if I
Just like erase part of the wire.
if I break the wire right there, then what's going to happen?
Well, then there'll just be sparks between.
Yeah, and if I break it so that there can't even be sparks, I hold the ends apart far enough, then the battery is just sitting there, but it's unconnected, so no current is running. So it's like a battery that's just not being used. Ben.
On power lines today,
Yeah.
aren't there things like that? Well, I see these things that look like.
Oh, they're not batteries. See, this was the first way that people figured out how to generate electric current. But we're going to learn there's even better ways. Because most of the electricity that comes out of our wall sockets is not generated from batteries.
Is the same as what is the electric current the same as what would come out of that?
Yeah, it's the exact electric current is electric current. We're going to find out. Now they didn't quite know that at this point, but they would figure that out pretty quick. But the but there's different ways of getting the electric current. One way, the battery way, is to generate it using a chemical reaction. But they're going to discover there's other ways to do it too. Now, before I go any further here, I wanted to get to Nick's question. What do you think of Franklin's theory in connection with this battery? Now, Franklin obviously came up with his theory before anybody invented the battery. Okay, but the question is, can his theory explain the operation of the battery? I mean, how would Franklin, using his theory, go about trying to understand what's happening in a battery? Daniel.
The bigger the stack, more electric fluid? Could it mean
Okay, now, but remember, in Franklin's theory, an object that is neutral, okay, has a balance, has the right amount of electric fluid, right? And it's, you get a flow of electricity when you have an imbalance of electric fluid. When you have one object that has too much electric fluid, say, and you connect it to another object that doesn't have enough electric fluid, well, then the excess electric fluid from one object will flow to the object that doesn't have enough electric fluid, right? Okay, that's the kind of explanation that Franklin had in mind for when electricity flowed between bodies. Troy.
Maybe like he thinks that like the metal stack is like either creating some electricity or like electrical fluid or making it go away and then it like continually flows.
Okay, now Troy, tell me if I'm misinterpreting what you said, but Troy says there's something special about this stack so that it creates electricity, the electric fluid. Now, what would Franklin say to that? Evan.
Well, didn't Franklin think that electricity could never be created?
Exactly. That was Franklin's like #1 principle in his theory, was you can't create this stuff and you can't annihilate it. There's the same amount of electrical fluid all the time. It just moves between bodies when there's an imbalance. Drew.
When like the battery isn't connected, won't it eventually wear out over time? Even if it's not connected?
Oh, yeah, it will. It takes a long time. But you're right, that there are, and that's a chemical process too. I mean, you can't, basically, the chemical reactions will take place at a very slow rate in this battery, and that's what will make the battery decay, even if you don't have it connected. Now, yeah, I'll take one more. Evan,
Maybe
do you have a?
somehow the solution that the cardboard has in it is when the solution maybe makes it have excess or somehow or no.
Yeah, see, now, I'm going to cut it off here because I think this is I mean, in a way, it's a trick question I'm asking you because you think I have in mind some way that Franklin could explain the operation of a battery, and basically what I'm going to tell you is I don't think he can. See, all of these, I mean, all the materials that are used to make this battery are all electrically neutral. Okay, there's nothing in Franklin's theory that, I mean, without modifying the theory significantly, there's nothing really in Franklin's theory that would account for why electricity would move from one neutral object to another. I mean, the movement of electricity in his theory is always due to some net imbalance. So you start out with a charged object that has too much electrical fluid or not enough electrical fluid, and then that causes the flow of electricity. But here, you're starting out with electrically neutral objects. And somehow, a certain arrangements of electrically neutral objects cause electricity to flow. But there's no reason why it should in Franklin's theory. It should just stay put because it's already you have objects that are in that right state of balance. In other words, that are non-electrically charged. Troy?
If you had like some static electricity that you got from rubbing,
Yeah.
and then put it in, and like just made like a circle of just like metal wire, and when you put it in, would it create electric current, or would it just stay there in the wire? Like if
If-
you transferred it to like a wire that's in a circle, would it just go? Or
You have a circular wire,
yeah.
and you say, take a charged object and touch it to that wire. Well, I mean, the electricity will leak off onto the wire where you touch it, and then there will be a moment when it moves enough to distribute itself evenly around the wire, basically. But that's it. It won't cause the current to continuously flow around the wire. Okay. So I think this battery, I mean, it's a good question that Nick asked, because that's always the way you should approach any subject is, you know, whenever you hear something new, try to relate it back to everything you've heard about it before. And if we take this this new invention of the electric battery and think about it in terms of Franklin's theory, seems to indicate that there's something basically missing from, something important missing from Franklin's theory, because there's no obvious explanation for how this battery could be working. Okay. Now, Ørsted was a Danish physicist, and he was very interested in electricity and magnetism, and he knew about these cases where, I mean, I told you about the case where lightning hit near the corner of this guy's house, and he had some old iron or steel knives in a box in that corner of the house, and they became magnetized. At least some of them did. And so there was a case where, you know, lightning is, which is an electric discharge, is causing a magnetic phenomenon. It's magnetizing steel or iron. Now, there were other examples of this. Sometimes lightning would hit ships at sea. Well, of course, these ships, they always carried magnetic compasses. And they noticed that if lightning hit the ship close to where a magnetic compass was, it could, I mean, there were cases in which it actually reversed the operation of the compass, so that the compass needle, instead of pointing north, now would point south.
It would still be right, it would just be backwards. So if you put the south up to the north, that would...
Right, right. Troy?
Would sailors realize this, or would they just go sailing in the wrong direction?
No, they weren't, they knew their directions well enough to know something had happened to their compass. So what they would do is just use magnets they had aboard to remagnetize the compass needle and fix the compass. But still, this was an unusual and unexpected phenomenon, that an electric discharge, which we can think of now as just a big electric current, right? I mean, it's just it's a big bolt of moving electricity. And that was causing steel and iron objects to become magnetized in ways that they weren't magnetized before. So that certainly indicates a connection between electricity and magnetism. Now, Ørsted wanted to discover that connection, learn more about it. And he tried running current through a wire and holding a magnetic compass needle, say that, like he one of the things that he tried early on that didn't really work for him was his compass needle is pointing, say, north. Okay, so this is north direction. And he tried, say, suspending a wire over it and running a current through that wire. Current is usually referred to as by the letter I by physicists, so I'm going to stick to that convention.
Why is that?
The other letters were used up, I guess. That's the best I can do. It's not obvious, is it? Troy?
Would we refer to him as like Ørsted, like we refer to Galvani as Galvani, or would we?
Yeah, no, I'm not on a first name basis with him, so I'm not going to call him Hans. We can just call him Ørsted. Nick.
Volta, did he discover the amount of electricity, or did they just later on look back and say, oh, we'll use this name?
Oh, yeah, I mean, what we call the volt today is really a measure, in effect, of the strength of the battery. You know, battery, you can buy 1.5 volt batteries or 9 volt batteries. And so I think that was an appropriate thing to name after Volta. Okay, now, so Ørsted has this idea that maybe electric currents will cause some magnetic effect that will deflect the needle of this compass. And so he tries this. I mean, he figures he should put the compass needle perpendicular to the wire, because what he expects to see is the compass needle like deflecting in the direction of the current. Okay, if there's any force that an electric current puts on a magnet, what he expects to see is a tendency for them to line up. Okay, so he tries this, doesn't work.
What way does it work?
Well, as I've drawn it here, with the wire, let me see, above. So the current carrying wire is suspended above the magnetic compass. It would have no effect at all, which is what Ørsted saw the first time he tried this.
Would you say that lightning, where if it strikes a certain area, that it would be very hot there for a few seconds when it strikes or something
Yeah,
like that?
yeah, there's definitely a
And
lot
you
of,
said that when a magnet is heated, it loses its power. So if
Right.
the lightning struck nearby a magnetic compass, do you think the magnet would lose its power and then maybe get a little confused and probably go the other way or something?
oh, that's interesting. Well, I mean, that's a great question. You're right that if the lightning actually hit, say, a piece of iron, it would heat it up so much that in that instant, when it was that hot, it wouldn't be magnetized. It'd be too hot to be magnetized. Now, it turns out that these iron or steel knives that I was telling you about earlier, they weren't directly hit by the lightning. The lightning just hit real close to them. And so there wasn't that kind of, heating effect where they were, if lightning had hit directly on something like that, it would actually melt it. And what they saw was not just these magnetic compasses, say, getting confused on the ship due to heating up. What they saw was that the compass still responded to the Earth's magnetic field, but in some cases it was completely reversed, so the north arrow would point south. So it was still magnetized. And the lightning effect on those knives that I told you about was to magnetize them. So clearly it's not just a heat effect. But you're right that Oersted thought that heat had something to do with it. So in that sense, you're on the right track. When he first tests this, and he sees that in this case that he tested, it doesn't deflect the needle along the direction of the current the way he had hoped. He thought, well, there's something missing in this case. Maybe in order to get this magnetic effect, you need more than just the current. People have seen this magnetic effect in these lightning cases that I've told you about. Well, there's more to lightning than just electricity. First of all, there's light, right? And then there's a lot of heat. So Oersted had the idea, well, maybe in addition to electricity, you need light and heat in order to get this magnetic effect. So one thing Oersted did was he made his wire really thin. Okay, now he knew from other experiments he had done on electricity and heat that if you made the wire really thin, the wire really heated up when you put current through it. This is how light bulbs work today, right? You're putting current through little tiny thin pieces of wire, and they heat up so much that they emit light. They glow. Well, so Oersted thought, well, this is the way to get all these effects. If I make my wire really thin and then put current through it, not only do I have current, but I have heat and light too. So maybe that will produce the magnetic effect. Nothing. Okay, so he's stuck. Now, Oersted taught at the University of Copenhagen. It's a university in Denmark. And he was physics professor there, and he taught classes on electricity, and he'd been studying the effect of electricity on heat. And the way that electricity, when you put it through a wire, heated up the wire, and that depended on the thickness of the wire. If you used a thick wire, it didn't heat up so much, but if you used a real thin wire, it would heat up a lot. Well, he was demonstrating this for a class. And he had a magnetic compass on his table. So, but this time his setup was just a little different than it had been before when he tried to see this effect. He had his big stack of batteries that he was using to put current through a relatively thick wire. And he had the wire suspended an inch or two above the table. Okay, so here's his wire. And this time, instead of in a east-west direction, he had it in a north-south direction. Okay, so that's north. He has his wire pointing in this north-south direction, and he's got a current going through it, say in this direction. And just by, more or less by accident, he had his compass underneath the wire. He wasn't really trying to demonstrate anything to his students with the compass because he had already looked for this effect of current on the compass and not been able to find it yet. But he just happened to have his wire draping over his compass. And so the compass needle, of course, is pointing north. So again, wire above, compass below. And he connects up his battery, so the current starts. And what do you think happens? Any guesses? Daniel. You had a 50-50 chance. Points west. All of a sudden, his compass needle jumps over. It doesn't point all the way west, but it's a definite, noticeable deflection to the west. Now that's strange. See, the reason he didn't find this before, one reason he didn't find this before, was he was expecting that if a current had an effect on the magnetized needle of the compass, the effect would be to pull the needle in the direction of the current. Now he finds the effect is the exact opposite of what he thought it would be. It actually seems to push the needle away from the direction of the current. Nick?
Could he try and could he push it east?
Yeah, he did try. He found. What do you think happened when, instead of having the compass below the wire, he held it above the wire? It actually deflects to the east now. Sure.
To realign his compass, could he like line up the current and then have the compass a little bit off if it was like pointing west? And would it go to the right direction north? If it's a little bit off.
If he did what, would it?
If he had the compass, it's still off pointing to the west.
Yeah.
And he puts it above his electrical current, would it go back and realign itself a little bit?
Oh, if he put it
If he took the
compass and put it where?
above the wire.
Oh, he
with
puts
the
it.
needle aligned to it, would it like go back north?
No, there's no. If he can't make it go to north. He can. Actually, it turns out that the reason the compass needle doesn't deflect completely west, say when it's below the current, is. Can you guess? Neve.
It's still trying to form. The Earth is still trying to make.
Yeah, the Earth is still exerting a magnetic force on it that is making it want to point north. I mean, the force from the Earth hasn't changed at all, right? Now, if you could somehow eliminate the Earth's magnetic field, then and just isolate the magnetic effect of the current, then he would have seen, and there's a later physicist that's going to show this, and I'll explain how, then he would have actually seen it just point straight west here. And then when he held it above the wire, would have pointed straight east. Troy.
Then why did they point south after the lightning came in?
Oh, I'll defer that question. But yes, it depends on how your compass is oriented with respect to the lightning bolt. So, Daniel.
You said something about how he was using a relatively thick wire when he was
Yeah,
does
yeah.
it have any effect if you used a thin wire?
Yeah, it turns out that what the other way that Oersted had prevented himself from making this discovery earlier was by using these thin wires. Because as he made the wire thinner and thinner, okay, what was he decreasing? The amount of current, of electrical current. Well, if the electrical current is what's causing this magnetic effect, as you decrease the current, you're going to get less of a magnetic effect. So he was actually making the experiment much harder by decreasing the thickness of his wire. What he should have been doing is using a stronger battery and a thicker wire to maximize the amount of current, and then that would maximize the amount of magnetic force that came from that current. Drew, you look unhappy.
I'm confused.
Well, somehow this current is causing a magnetic force, a force on a magnet. Right? I mean, that's what this little magnetic compass needle is. It's a magnet. And it's doing it. So it's exerting a force on it. Now, if a current exerts a force on a magnet, well, it makes sense that more current would exert more force, right? Okay, so that's why I was just making the point that when Oersted started out using really thin wires, what he was doing was decreasing the amount of current, right, by using these skinny little wires. And then he was decreasing the magnetic force created by that current. So that's why he couldn't find it. Okay? Troy.
If he had it not aligned with the needle, like the electric current, and had a really thick wire, would it have done anything? Would it have a...
Well, that's the thing. You have to have two things right here in order to see the effect. You have to have a good-sized current fairly close to your magnetic compass, and you have to have the orientation of the magnetic compass and the current be right. And he managed to get this right for the first time in a class while he's doing a demonstration for students, and he's not even looking for this effect. And it was by far the most important discovery that he made in his entire life. And he made it in a lecture. Now, in that respect, I've been letting you down this year because I've given all these classes and I haven't discovered anything. But Oersted is the only person I know of to have made a major scientific discovery in a class demonstration by accident.